Okay, so hello there. I am Arya, not that one. And today we'll be deriving the general heat conduction equation, which is the Cartesian coordinate system. So let's start with considering a control volume, a cubical control volume in Cartesian coordinate system, which is basically XYZ axis. Uh, and let's say heat travels in the x direction perpendicular to YZ plane. Let me actually label this. It's Z here. So X, Y, Z, and heat is entering perpendicular to the YZ plane. So let's start. So for this direction, we'll be starting from uh, energy balance, which is basically the most important thing in thermodynamics and all. So yeah, energy balance equation goes like this, which is energy rate of change of energy in plus rate of change of energy generated is equals to rate of change of energy uh, out plus rate of change of energy stored or accumulated. Okay, so from here on, if I call this E dot as energy, it still means it is rate of change of energy because dot represents with respect to time. And if I just call it energy, just understand that. Okay, so now also you can understand this energy balance with an example of, like, let's say a container being filled with water, right? So water entering the container is basically energy entering. Then let's say somehow miraculously the container is generating its own water. Yeah, so that is basically energy generation. Then uh, after container being filled, the water flows outwards. That is basically energy out. And container is being filled, right? So whatever water is being filled has been filled in the container is energy stored. So that is one way to, like, understand energy balance in simple terms. It doesn't has to be like 100. It's just an analogy. Okay. uh so yeah, let's start with each terms of this equation of energy balance. So let's start with energy in. So here in our case, we are considering heat as the form of energy. So whatever in the control volume, whatever heat is entering, which is Q dot, that's Q dot in x direction. So that's gonna be our energy entry. So energy in is Q dot in x direction. Next term is energy out. Okay. So here energy exiting the control volume is gonna be Q dot x, which was energy entered, then plus, yeah, then plus rate of energy change with respect to a distance, right, with respect to x direction, which is dou q dot upon dou x into whatever the distance was there, which is dx. So here in our control volume, the distance in x direction is going to be dx, distance in y direction is going to be dy, distance in z is going to be dz, right? So that is energy out, and that is energy in. So energy out is going to be q dot x plus dou q dot upon dou x dot dx. So okay, also let's change our energy balance equation to something which we are gonna be needing, which is basically take energy out from right side of the equation to the left side of the equation side. So it becomes energy in minus energy out plus energy generation is equals to energy stored. Yeah, this is a new equation that we need and further calculations. Okay, so now let's calculate the term energy in. This was in x direction. Energy out is also in x direction. So let's calculate energy in minus energy out in x direction, which is going to be the above equations. subtracting above equation, q dot x minus of q dot x plus dou q dot upon dou x dot dx. Yeah, and from this equation we can see that this and this q dot gets cancelled, and this plus becomes minus due to the minus sign. So energy in minus energy out in x direction is equals to uh, minus of dou q dot dou x q dot dx. This is our energy in minus energy out, rate of energy. Uh, so now let's from Fourier's law, because we are this is conduction. So by Fourier's law, we'll write the value of q, which is minus k in x direction, conductivity in x direction, into area into dt upon dx. This is by Fourier's law. And let's replace this q dot in the above equation. So the equation becomes energy in minus energy out in x direction is equals to minus dou upon dou x minus dou upon dou x minus kx a dot dt upon dx. Now here area, perpendicular area to the heat flow, is gonna be dy into dx, sorry, dy into dz. Yeah, uh, in yz plane, right? So equation becomes energy in minus energy out in x direction is equals to minus dou upon dou x minus kx dy dz. Yeah, here, sorry, here in in q dot by Fourier's law, it's gonna be dou, not dx. So it's dou t upon dou x. And here also, let me change it here as well. Right. So it's gonna be dou t upon dou x, and I think I also missed this dx right here. So into dx. Yep. Into dou t upon dou x into dx. So this equation becomes the this equation becomes the final equation in x direction. So similarly, let me draw like proper box. Yep. This equation becomes the equation in x direction. Wow, what the hell just happened? Now, similarly, we will have the same equation in y direction and z direction as well. Let me write this as equation 1. Then let's write it in y direction and z direction as well, which is, let me change the color actually. And let me write the whole thing once again, so it will be easy for us to understand further. Okay, sorry, I'm using this app for the first time, so it's kind of confusing right now. Yeah, so the new equation becomes first energy in minus energy out in x direction is equals to minus dou upon dou x. You know what? Let's say see here in this equation, minus minus sign gets cancelled. This color is not good, I guess. Let me change the color once again. Go for, let's go with this color. Okay, so minus minus sign gets cancelled here. So energy in minus energy out in x direction is equals to, this is plus dou upon dou dou x, kx dot area was dy dot dz, but dou t upon dou x dot dx. Right. This was equation 1. Then energy in minus energy out in y direction is equals to dou upon dou y, k in y direction, dx dot dz, dou t upon dou y dot dy. This is equation 2. Then energy in minus energy out in z direction is equals to dou upon dou z, kz dx dy dou t upon dou z dot dz. Okay. So these are the three equations. So this is adding these three equations, we'll be getting total energy in the system. Because in this consideration was only heat flowing in x direction, but in general case, heat direction will flow in all three directions, x, y, and z. So adding this, we'll get a total energy in minus total energy out. So now next term. Uh, Yep. So next terms are gonna be energy generated and energy stored, right? So let's go with energy. Color looks same. I wanted to change the color, so it will be it will look equations would separate, right? So energy generated, right? Energy generated is basically gonna be volumetric heat generation. That is heat generated for some volume into volume. So it's pretty much gonna be just like Q dot G into dV. This dV is volume. Okay, let me write here. dV is equals to dx dot dy dot dz. This is basically the volume of control volume. Control volume, total volume. Yep, that's volume. So this is energy generation. Uh, let me number this as equation number 4. And then the next thing is energy stored. Energy stored is basically a rate of change of internal energy. It is going to be dou upon dou tau. Your tau is time and t is temperature in the whole equations. So yeah, dou tau m c t. Right. This is going to be equation number 5, where u is equals to m c t. U is internal energy. Okay. Uh, So finally, we have everything that we need right here. So putting all 1, 2, 3, 4, 5, all these 5 questions in the first energy balance. This one will be getting. Let me change color once again, just so it looks better. Now final one should be in like better color. Yep, this color. Yeah, so the final equation is gonna be this way: tau upon dou x kx dot dy dot dz dot dt. Sorry, dou t, not dt. Dou t upon dou x dot dx plus dou upon dou y ky dou x dx dz dou t upon dou y dot dy plus dou upon dou z kz dx dy dou t upon dou z dot dz. These are all the terms. Let me just change Let me just make some space for the whole equation. Okay. So T is this was all total energy plus. Now let me change the color once again. So final equation would look nice. Plus now in energy generation, which is Q dot G dot dV volume is equals to, let me change color once again. Let's go with blue, is equals to dou upon tau mct. Okay, this is the final equation, the final general heat conduction equation. Now, by applying different cases, we get different variations of the heat conduction equation. But as you can see in this, let me explain what all terms are. So this is basically stored, energy stored term. Then the purple one, it's pretty much energy generation term, and the whole red thing, this part is energy in minus energy out total. So this makes the general heat conduction equation. Now let's discuss. Let's discuss. Let me just change this in this way. So let's discuss different conditions. Okay. So let me change the color again. Damn. So the first condition is all the properties are same in all directions, which is basically isotropic. So kx, ky, and kz. Kx, ky, and kz all are equal. Okay. Also, let me change one more thing, which is uh, you notice that there is dy, dx, dz, dx. Here also dx, dz, dy. It's present in all the terms, right? Here also it's dv, which is pretty much volume, which is dx dot dy dot dz, right? And here in stored, this m is basically mass is basically density into volume. So volume term is present in all the terms. So we can just eliminate volume from this completely, right? So let me erase all this and let's just cancel out all the volume terms, and finally we'll get, and considering the control volume as isentropic, which is kx equals to ky is equals to kz is equals to k, this, and then uh, removing dv, canceling dv basically from equation, we get tau upon tau x k tau upon tau t upon tau x plus tau upon tau y k tau t upon tau y plus tau upon tau z k tau t upon tau z plus q generation, energy generation, is equals to tau upon tau bracket m changes into rho ct. This is the equation we get, and you can notice that if we remove k term from all these three equations, then we'll get the square derivative, or we'll basically get del operator here, right? So let's take out the k as common from all the terms, and then divide the whole equation by k, and we'll get tau upon tau x. K is removed and divided. Although let's write it in steps. Okay, so we took out the k common, tau upon tau x, dou t upon dou x plus dou upon dou y, dou t upon dou y plus dou upon dou z, dou t upon dou z. This is the whole equation plus q dot generation is equals to dou upon dou ta rho ct upon rho ct upon well wait rho ct. C is also constant here and rho is also constant here, so these two can be just taken outside because this because we are considering all the properties are same. Let me just rewrite this. Rho c dou t upon dou tau. Okay, this is the new equation we get, and then after this we divide the whole equation by k, and we get dou upon dou square upon dou x square t plus dou square upon dou y square of t plus dou square upon dou z square of t. This is pretty much del operator, and as you can see all the denominators were same. So plus q dot generated upon k is equals to rho c upon k dou t upon dou tau. Okay, here this part is known as uh, well, inverse of this is known as thermal diffusivity. So basically this part is 1 upon alpha, where alpha is diffusivity, thermal diffusivity. Yeah, and the starting part can be written as del operator. Del operator is basically, well, del squared operator, not del operator. Del square of t, where del square is dou square upon dou x of plus dou square upon dou y plus dou square upon dou z. So when we apply del operator of on t, we get the initial, well, the starting of this equation. So it becomes del square t plus q dot generation upon k is equals to 1 upon alpha dou t upon dou ta. This is the next equation that we get. Let me actually write what del operator means as well. So del is basically, del operator is basically dou upon dou x of I cap plus dou upon dou y of function j cap plus dou upon dou z k cap. So well, if we square this operator, you'll see that I into I becomes 1, j into j cap into j cap becomes 1, k cap into k cap becomes 1, and the operator is squared basically. Yeah, so that's how we get this del square del square operator here. Now in this equation, I'll explain all the terms. So this is, yep, so this is basically energy in minus energy out term. I mean, it's present every time. I mean, for the next conditions, right? So this is present all the time. Then this term is defined by not defined by, it's like internal generation, and this term is for steady state term. This is internal heat generation, and this is present every time for the next cases. Like there are next three cases, which is like internal heat generation, without internal heat generation, and then steady state, unsteady state, right? So if it's internal heat with internal heat generation, then this term heat generation term exists. If it's no internal heat generation term, then the term becomes zero. If it's steady state, then this term exists. If it's not steady state, then term becomes zero. Let me actually write those all. I'll write them as the cases. Okay, so let's discuss all the cases. So also here, when I wrote this steady state term, this internal heat generation term, this is for understanding. This is not exactly. So let's discuss all those cases. The first here, this case, or the base equation is for uh, un, unsteady and internal heat generation. Yep, the main equation was for that. Then case one, which is for uh, steady state, steady state plus no internal heat generation. Right here, the equation becomes actually, sorry, the equation becomes del square T, no internal heat generation, so the heat generation term becomes zero, and it's steady state. So in steady state, the steady state term also becomes zero because there's no change in internal energy with respect to time. Mm. Okay, so now let's go for case two, which is steady state plus internal heat generation. So here steady state term becomes zero because uh, del square T remains. Then internal heat generation term exists because there is internal heat generation, that is Q dot G upon K is equals to the steady state term becomes zero because it's in steady state, so there's no uh, rate of change. I mean, there's no change with respect to time in internal energy. Again, I'm telling you that I wrote the steady state just for understanding. This is not exactly that term. And then case three, this is basically unsteady, no internal heat generation. Unsteady plus no internal heat. Right, so here equation becomes del square T of no internal heat generation. So heat generation term becomes zero is equals to, but it's unsteady, so the term exists 1 upon alpha dou T upon dou tau. This is the final. So yeah, this is the final equations, final cases and equations. Mm, I'll make a video and like how we use this general heat conduction equation for solving something else. It's like let's say we can use this general heat conduction equation to solve for temperature with respect to distance, to find temperature with respect to distance. I'll upload that video next time. And yeah, this was pretty much my first video where I'm trying to teach something. So let me know for any like if you have any suggestions for me to do any videos that you want, or like any feedback on this, like if I should change something. Yeah, that's all. Thank you for watching. I hope you like this. Also, I'll try to be less unhinged. I mean, sorry, I'm more unhinged. Okay. Also, I'll try to be more unhinged because I'm not making this channel to be some sort of teacher or something. I just wanna have fun with this. Yeah, that's all. Thanks.